Hello. The audio will be recorded. It should be, because that's not the host area. Sorry. The audio will still be recorded, right? That doesn't record, it goes through this. I just want to make sure. You have this link. Zoom link. Let me do it. Hello. All right, we can start now. Sorry for the sound. So finally, we are ready to do what we wanted to do. So today we will talk about let's start with the Yes. X. At each point does the same thing. This keeps replicating. So it's not this. So X is the distribution. X distribution. Number of and Zn is the number of what's happening? Starting from this one, each node is going to give rise to X number of children, where X is a random variable, identically distributed for every single one. So this guy gives rise to, let's say, 3. And this guy will use the same distribution as the first one used. So suppose this is 4, so this gives rise to 4. And you're essentially using the same distribution to create more and more children from 3 generation. This process goes on forever. Number of nodes and children. So number of, you can call it children.
What I'm not understanding is that how do you define a level?
So this is level 0, this is level 1, this is level 2.
So at level 1, so let's say you have from level 0, you are like have 3 branches.
Yes.
And at level 1, all of those branches will give rise to some branch.
Each one is going to do the same thing. Every same process is repeated as well. Same process is repeated and each one. So this is my level 1. So this in some sense you can call it ancestry. Okay. So if I tell you one child, what's the level of it starting from the starting? How many levels down has? So what is the first question that comes to mind if I have to define such a process? So X is distributed as everything is IID, everything is independent. So every time this generation is happening, it's independent of everything else that is happening. But Zns are not independent across. So Zn and Zn minus 1 is not independent. That will critically depends on Zn minus 1. So what is a reasonable question to ask?
Is there any reason to call it critically dependent?
No, critical is just a normal English people. We'll come to criticality later. In this course, there are lots of critical parameters where you want to study phase transitions. Those criticalities will be there. So, what's the most reasonable and simplest question one would like to ask? So, this is given to you. Oh, this is given. So, D is given to you to begin with, and this process is replicated over and over.
So this is also a random variable. So you can ask the distribution what will be the level.
So question number 1. Distribution. There. Oh, okay. What about constants?
If Zn a Martin,
Oh, that's too complicated question. One could ask that question, but too complicated. You just level 101. So what's the simplest question you would ask?
So you have a sequence of Zn, let's say. So you can ask whether it is converging or not.
Yeah, in this process, what does it mean that Zn converges? It has a very peculiar meaning.
Zm will be equal to Zm minus 1. The same
By definition.
That's the convergence.
That's by definition. But what does it mean for this process? Suppose Zns converge. What is happening to the process?
So like there is I mean like after a certain point there is not much of branching. Like
So will that happen? That's the point.
I don't think it will. Yeah. So it's I was saying that it will never converge.
No, I'm not saying. Suppose it converges.
Okay.
What do you expect to happen? What does it even mean for this process?
So probably it will stop after some.
Okay, so what? Yeah, that's precisely my point. That what does it imply?
So there's a stopping end.
At which what happens?
So to go back to the definition.
Last right here.
Last child will not give further knowledge.
No, so think of when does this process stop? It stops as soon as Z becomes 0 for some n.
Yeah.
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 It's a positive probability. Nothing is born at particular level.
Yeah.
So is that what will get implied if Z were to converge?
Could also be convergent to 1. If it's always, there is always 1.
Yeah.
So
So
let's take the degenerate case out. So that's one degenerate case you have to always keep outside. That probability of x equal to 1 is 1. That's a degenerate case. That this one dimensional thing just keeps growing.
Yeah.
So that you have to keep outside.
If you don't have that, then if it converges, it should go to 0.
Okay. So is everybody on board? Should I define what you do now?
Wait,
So we started with the starting node. This is started. This is going to give rise to x number of children. Where x is a random variable,
okay,
which has a particular distribution given to you.
okay,
And now this process is repeated for every child as we go down the generation.
okay,
That's all. So Zn is the number of children to be born at level n. So we're starting from 1 and we want to look at how does Zn evolve. That's the essentially distribution of Zn means. I'm just trying to develop some reasonable questions to ask for this problem. What else could be a reasonable question to ask? So distribution of Z is definitely a reasonable question to ask. Now, can you refine what you said? If Zn converges, what does it imply?
So the converging distribution
The whole process is clear.
Yeah.
What is going? It's a very simple process. It's like the starting point for many difficult things. So what we'll end up doing is we'll look at complicated processes and either lower bounded by this process or upper bounded by this process for a particular distribution. This we will eventually figure out how to handle this exactly. Many other complicated processes will not be able to do it exactly. So what we'll try to do, if there are X number of particles in my difficult process, I will say there are at least X number of particles in my this process. And now exactly I know when does that X happen for this process. So that will translate to my difficult process. Okay. So I'll have to appropriately find a branching process which either lower bounds it or upper bounds it.
Okay.
And we'll try to sandwich it between two different branching processes. And for this, we will get some concrete answers. So it's a very foundational in the sense. It's also easy. It's not very difficult. What we want to do, at least today, it's pretty straightforward. But I want you to think about what kind of question would you like to ask. What is the first obvious question you would like to ask? If you ask this to a 10 standard, if you give this to a 10 standard student, he'll say essentially this just goes on forever.
and what distribution of X this
X is given to you. Distribution of these given.
The question I would like to ask is that for what distribution of X this branching process dies out
Right.
or becomes a very big.
So that's a good question. We'll try to define it even further. What is the expected value of X for which the process dies out or lives forever?
Yes.
Distribution is more complicated. It will turn out that expected values are sufficient to characterize everything. It will not matter what the distribution really is. So what does it even mean that something dies out? Can you mathematically define? Then we can put a probability to that event. So what is the event that the process dies out in terms of everything I've defined? There exists an event
Yeah.
such that Zn is 0. So it's more complicated. It's not just that Zn equal to 0. Because this process just continues forever.
Yeah.
We know that once it happens, it's always going to remain 0. That also we know.
Yes.
So you're looking for there exists an event such that Zn equal. So that's the event. Which you do. So Finally, what is extension? Divide this. That exists then n. And the probability of this is probably going to find as p. There is 7. So this is the object of interest rate. We want to find when is eta 0, when is eta 1, depending on the distribution of x. So now any hacks, I don't want solid argument, I at least want some intuition to suggest in terms of the expected value of x, what can you say about eta? If I give you expected value of x, is given to you, and suppose it's less than 1. What can you say about it?
So the n plus 1 is expected value of x times z. Is it
Yeah, that's correct.
correct, right?
But that's a slightly complicated statement to make. Because you have to condition. So Zn and Zn plus 1 are not independent of each other.
Yeah.
So you'll have to take a little bit of care to do that. But because I'm asking you to throw your hands around, it's okay for the moment.
So again, tell me what is the question?
So the question, one way to think about it is that suppose I give you the expected value of x, given that it is less than 1.
Okay, so it's also given.
It's also given that it's less than 1.
Okay.
What do you expect eta to be?
It is the probability that
Probability of extinction. So this, I believe, you should be able to say something interesting.
it should be 1, right?
No, so don't answer me in terms of another question.
If it dies out,
I don't know that. All I'm asking is, given that the expected value of x is less than 1, what is your guess for eta, and where is that guess coming from? I want you to generate intuition for yourself before I give you something concrete.
so maybe it's too naive, but as the expectation value is less than 1, I can think of this branching process as like exponentially growing.
Growing or dying?
Like number of nodes are like exponentially growing. Sorry. So like the branching is happening to, let's say it's happening for a very long time.
But that is a function of expected value of x. So you can't take that out of the picture. Right. The level at which this process will grow depends on the expected value of x.
Yeah, so it's like what I'm thinking, like somehow I can connect it with like exponential to the power negative value. Expected value.
I don't see that making more difference.
So if expectation is less than 1, and if I suppose I start with n nodes,
No, you're starting with 1. Process is fixed. You're not changing the process.
for large enough n, it will die out, surely die out. Right?
Okay, so I want some argument. I'm not asking for a watertight argument. Where is this coming from? Where is this?
So you at n level you have this n number of x's, right? No, because
It depends on Zn minus 1.
okay. But what I'm saying that if you are, let's say you have this level, it's level 1, right?
Yeah.
So you have this 3.
That's just an example.
Yeah, but
This is not what is going to happen every time. This is an example for a particular realization of the random variable. Now we're saying that suppose the expected value of x is less than 1. So on average, how many edges you're going to see coming out? Less than 1 from each node. Can you build an argument to suggest that eta is either 1 or it's close to 1? I'm okay. Can you improve it's greater than 0.5? I don't mind. Anything greater than any constant.
Okay.
Taking a little more time just for you to think about it yourself before. So certain quantities when expected value of x is less than 1 should be easy to compute. What are those quantities which will tell us?
X can take values either like discrete values like 0 or 1, or like it cannot be negative as well. So since the expected value of x is less than 1,
Build it.
so like on an after few steps, after few levels, we can say that the number of nodes coming out from a parent will be less than one. So basically that means zero. It should be.
But that is true for level 1 itself.
Yeah.
You just use a little bit. Whatever you said is correct. Don't say it's less than 1. It's something less, something smaller than something. So as the number of levels progress, that shrinks. Somehow you have to say that.
Okay.
So like
What is shrinking?
the number of nodes from like what's like its parent had, I mean, like in that level. So then in the next level, the number of nodes are decreasing from its previous level.
Is that correct?
It will remain on an average. So with positive probability, x is equal to 0. Positive probability.
Yes.
That's what we can say. If
That is true.
then
But that doesn't imply anything. That's little too weak. You have more power associated given to you. So probably you're on the right track. So don't say less than 1. It's less than something else, which is stronger than 1. And once you see that, then just summing it over all n. See, somehow you want a converging. See, so why is it what is the simplest series which converges?
geometric.
Yeah. So what is geometry here? Something is geometric. Something is decreasing geometrically when expected value of x is less than 1.
Suppose so we'll have multiple cases, like x could be 0, 1. Suppose
It could be 2 also. All I'm giving you is expected value is less than 1. But if you can build an argument with just 0, 1, sure, go ahead.
So what if we look at the probability that it never gets 16?
Okay. 0, 1 will have some binomial or type of probability, right? Like first, like if it dies at the first node, okay, or it dies after the second node, or it dies after the third node. So 0 then second. No, but it will convert.
There is a probability to die out at the starting point also. Right. X is less than.
But that is anyway we're looking for n eta close to 1. So that is of course there. See, nobody in this world can say that it will always grow. Because at 0 itself, x can take a value 0. So that is always there. But that is a 1 minus eta, the complement. Here we are looking for a diagram. So it's definitely dominated by that. So whatever is the probability of dying there is definitely that much eta is better than that probability. Dying at level 0 itself. So you add, if it doesn't die here, what is the probability of dying here? And this just keeps going on.
I cannot do this interesting, like Z0 is 1, Z1 is expectation.
Z0 is 0. Yes, Z1 is 1.
Z1 is expectation value of x times Z0.
Okay, but that's not Z. Then you have to start with 1.
Yes, yes.
Yeah, that's all.
So probability of x being 0 is higher than the probability of x being any other positive value other than 0. Like 1, 2, 3.
Fine, okay, if that is true. I'm not going to argue that it's true or not. Suppose that's true. What do you get out of this?
Means for expected value to be less than 1, this must be true.
Yeah, but
And so finally there will be a time coming when
you will understand this is the non-triviality of it. Even though the probability that that's 0 is finite, but the process is just blowing out very quickly. So you have to understand the rate at which both things are happening. It's not a trivial answer saying if probability of 0 is greater than 0, it definitely dies out. That's not true. So we'll also come up with the reverse argument where the expected value is greater than x and the survival probability is definitely greater than 0. That's not even true. We have to worry about how much it has blown up by level n. But let's do some simple things. Before we do just to get our values 30 and try to be good. So what will I write Zn as in terms of Zn minus 1 and x's? And x r I equal to 1 to Zn minus 1. This one is correct. Not multiplication. It's not a multiplication. If there is minus 1 particles are there at level n minus 1. Each of them are going to give rise to x. For each x either independent and distributed in This is just by definition. Now, what is the expected value of that? It's easy, but you do notice something. It's not obviously something. It's notice something and then write down the expected value of Zn in terms of expected value of xr. You agree to this? Everybody understood this? I want an answer in terms of expected value. There exists. Like the number of particles and growth on every other one.
Isn't it just the number of particles you had in n minus 1 level and multiplied in this because of this? Because if your x's are independent,
Excited. So what do I have to do to write it? I want a simple expression for expected value of the See, what is this? It is sum of independent random variables, but the number of summands is also random.
it's dependent on the previous value.
This and this, yeah. These are actually independent of this, but the number of summands are random variables. That's the only care you will take. So how do I handle this? I want to write this only in terms of expected value. There are many names for it. Sometimes it's also called voice identity, but you don't really need a sophisticated man to write this.
Usually give the total number of nodes.
So, one thing, ask one thing that this I is running from 1 to Zn minus 1, and this Zn minus 1 you don't have that information, right? So you have to use conditional probability or something.
Why prospect? Conditional expression. Suppose that are conditional Zn minus 1. What is the expected value?
Again, what?
Zn given Zn minus 2. Okay, then.
Yes,
I'm fixing this. Now it's no longer the random variable. Then what is the expectation? Just linearity expectation will give me
Zn minus 1 multiplied.
expected value of x. Now I am into unconditional. What do I get?
Oh, intersection.
Oh. Just take the expectation of this. This is a constant.
Yeah.
So you, all you end up getting is Zn minus 2. Let me call this mu for time. Simplicity for the rest. What is the relation value? What is the expected value of Zn? Only in terms of expected value.
So it will continue, right?
Yeah, just tell me what is equal to in terms of mu alone. This is what you are going to use. You said it's less than 1. It's much smaller than that.
This is what I was saying. If Zn plus 1 is expectation of x times Zn.
See, that's what I don't want you to do. You have to do this one step. The product is not true. You have to take care in doing what you're doing. Simply, this relationship is true, but that doesn't mean if these are independent of each other. What you're saying is not correct. It's critically important that once I condition on this, you get independent.
Yeah.
Some care, but thing is reasonably simple. Okay, so now can you tell me something about eta? Eta, remember the probability. What is the line? It has the probability that there exists and such that there will become 0. Extension probability.
What is the question?
The question is, now that we have computed what is the expected value of ZNS, and this seems to be shrinking very fast.
Yeah.
Mu is less than 1.
Yeah.
So this is going down remarkably fast. What is eta? Can you give me an estimate on eta?
Minus 2 raised to n.
See, n has to disappear. First of all, whatever estimate of eta you are going to give, it cannot be a function of n. Because by definition, eta means that there exists an n.
So maybe exponential to the power e.
You think, don't jump too much. Whatever we got,
Yeah.
that at level n, the expected number of particles I'm going to see is mu to the power n. So how many total particles I'm going to see throughout? If I were to sum across all generations, what is the expected number of children I'm going to see? Expected value is Z0 plus Z1 plus Z2 to all the way to pushing to infinity. So what is that summation given that this value is put to the power n? And mu is less than 1.
1 plus mu plus mu.
Yeah. But what is that sum? We know that series converges.
Yes. 1 minus mu.
So it is 1 over 1 minus mu.
Yeah.
So the total number of, so let's call it T. T is it's not there. What are you telling us? The direct conversion. Now can you tell me? Now you can make all your arguments really justifiable. All of you wanted to say that if mu is less than 1, eta is close to 1. Does this have any implication towards that? What is this saying? The total number of particles I am going to see across all generations on average is bounded. So what is the probability that I see more than these many particles? Now you should be able to at least estimate something. Is T clear? Right? What is T?
Yeah.
T is the total number of particles I'm ever going to see. And this is clearly bounded. The expected value of T is clearly bounded.
Yes.
So what does it mean? Throughout the generation, the total number of particles I'm going to see is bounded. On expectation. So what is the probability that I deviate from the mean? That is generally not, but it's always hard. We did last 3-4 classes worrying about Markovs, Chebyshev, Chernovs, and last Azumov. They're not trivial. They're not difficult, but they're not trivial. Half is not a good estimate. If half was the right answer, we all would have gone on. Because if no convergence happens as a function of n, no communication system would have worked, no information theory would have been developed, no simulations would have run. Because the whole point of simulation learning is that the error as a function of time actually goes down. Otherwise, fine. Your simulation, my simulation never going to match. So the whole point is that there is an exponential tail generally, what you have been saying. So I'm not even caring about exponential tail. But use whatever inequality you know. Can you give me an estimate on eta? At least in your head, you should be telling yourself that eta is close to 1. Or at least I can give an estimate of eta.
Yeah.
Can you give me an estimate of eta as a function of mu? Let's try to do that. Eta, everybody remembers. Should I go back? Eta is the probability that there exists an n such that no more probability. Eta itself is the probability.
Okay.
It is the measure of
The question.
So now, if the total number of particles across the whole thing is bounded, what does it mean in terms of eta?
So like at certain in
So if expected value of t, so suppose t was, if I tell you that t is bounded, what does it imply in terms of eta?
Eta is one.
Eta is 1. I'm not able to tell you that t is bounded, but I'm able to tell you the expected value of t is bounded. So what is the perturbation of a random variable around its mean? That is what all these inequalities control.
Yeah, I mean, it should exponentially decay.
Not always.
But it should.
Marcos doesn't tell you exponential decay. Marcos inequality only tells you that what is the probability that x is greater than expected value of x. Is only going down is how much? Expected value of that divided by the deviation. That's not exponential. You can improve it, that's different. But not every inequality is exponential in nature. But there is some connection. I just want you to come to, I don't want to write it. I can write it. But at least you should appreciate by this time that given that we have been able to control the expected value of t, it does tell us something about t, and because of that tells us something about the eta. Because if t was bounded, eta is bounded. What have I shown? That expected value of t is bounded. So t should not be too far away from it. So what is the probability that t and expected value of t are larger than n? What is the probability? Let's say x, don't say n is this. So what is the probability? This is really back of the envelope. T minus is greater than x. I know how much is this. So what does it tell you that whatever probability bound you're going to get, t is.
So you can express it like 1 minus p of less than x.
Yeah.
And what is the Markov-Nicolai test?
See, two, three things you should not forget in this book. Because this Markov is inequality. One is Jensen is inequality. Rest of it can be derived. So I don't even want a precise answer. But we know all these inequalities are of this type. What is the perturbation or deviation of a random variable from its mean is controllable. And just something like not precise, but something like 1 over x. You can also technically use function of this.
Yeah.
Now can you say something about eta? I already have a control over expected value of t. Now, spending a long period, it might appear that I'm doing this over and over, but I just want you to have a feel for it because the proof we are going to do will not give you any feel for it. It will be just mathematical manipulations of some fixed point equations.
Maybe that t is infinite is 0.
It's not 0. It's tending to 0. Yes. So as I increases, this goes down.
Yeah.
So now, given that this is finite or bounded, it's pretty unlikely that t is going to be unbounded. So you can actually control what is the probability that t is greater than whatever number you want. Because this is bounded. And that directly translates to eta itself. Because if t is bounded, this is
T is bounded, it is equal.
t bounded. Guys, what you're able to say here is that what is the probability that t is bounded? That exactly is eta. That okay? Where this is true. So if t is bounded is let's say probability 0.5. What is the probability eta? It's exactly 0.5. Yes. So with that probability, there exists an n such that zero becomes 0. Because otherwise it won't be bounded. So this exactly this probability is a bound of eta. It's not the tightest form, but it's a boundary. So at least in the case when how did you write this equation?
P minus
This one?
yeah.
This is just the usual Markov inequality, Chebyshev inequality, any inequality. I'm not even writing the precise form. They have this form that in x it decreases with this, in expected value of t it increases. You can choose your favorite one. I don't care. These are nothing but deviations. So any random variable deviates from the mean, it has a tail. Otherwise, there is no justice in this world. So if expected value doesn't respect expected value, what kind of random variable? Maybe they will have a problem, but that's very not very good.
Okay, so can you please repeat the entire
Okay, very good. So what have you got here? You got expected value of t is bounded. If t was deterministic, then also tells you that t itself is bounded. But these are random variable. So I can't directly claim from here that eta is bounded. But what can I do? I can try to control how far actual t, which is a random variable, deviates from its mean. And that I know for like this. I also know that if t is bounded, then eta is 1. So from there, I'm going to get the probability that t is bounded. And that is exactly going to be a lower bound of eta. So as long as mu is less than 1, things are not too difficult. You can come with your favorite inequality here, you get the appropriate bound. What will actually show is that eta is 1 as long as mu is less than 1. That's what the punchline is. It's not 0.5 or 0.75, it is 1. There is no other way. But the intuition is essentially this, that as long as mu is 1, t essentially is a bounded. Expected value of t is bounded. That essentially should tell you that process is shrinking and finishing very fast in some sense. Okay, so now let's come to the brutal proof. Any questions? Consume process. Equal to 1. Now, what condition do I have to put? Claiming eta is 1, even when expected value of x is equal to 1. So I need to say something, otherwise, this is not going to be true because I can always say x equal to 1 with probability 1. So I need to avoid something. The third statement is not true for a particular distribution where x only takes value 1. With probability 1. So it will be just the same. I just keep generating 1 at a time. So this is never, eta is never going to be. So what should I avoid? Then expected value x is 1 and what has to come? Probability x equal to 0 is positive. That's maybe another way of putting it. But x equal to 1. Then it's get implied values. So we have some meaning for this. This also makes sense. Now try to build an intuition for this. That if expected value of x is strictly greater than 1, why should eta be less than 1? Go to 0. Right? Or be able to argue is less than 1. It's essentially positive probability. It just keeps going. That's what that means. Eta is the extinction probability. So 1 minus eta is the probability that it survives forever. So that I really need to think about it, because otherwise I can finish the book. Okay, so what are we going to do? And we'll actually characterize exactly what the solution of the data is. And from that we'll get the answer. So it's slightly more than, so it's not only an argument saying it has to be, it actually give you a solution, and that solution does not do. Okay, so this is the quantity we want to use very extensively. What name do you know this by? You don't know it. This quantity, have you ever seen this quantity? What do you call it? Characteristic function. I don't know what you call it. The book calls it the derivative. Probability generating. We want to see the whole process. Okay, so let's start. So eta remember is the probability that it is. There is this n over there. So eta n is the probability that ZL is. Now think of this event. Zn equal to 0. And what is the relationship between these two events? What is eta is equal to 0? Eta n. So eta is probability that there exists an n. Eta n is the probability that ZL itself is 0. I mean, at a given, like you are projection, fix an n. For every n, I can define this function. Now I can also look at the events. ZL equal to 0 and ZL plus n equal to 0. Is the relationship between the two? You will always have to take place, right? It's like this happens definitely. Oh, so how many will know continuity of probability? Oh. So what we really want is, okay. Oh, I'll do it. Yes. So I knew that somebody might not know, so I have to dig out the simplest proof for this. Okay. So what do I really want is I want to claim that eta n goes to. That's what I want to claim. For n goes to because of this, these are increasing ones. So as an aside, what we want to do is important. So let n is such that I want to show you that the union what should this probability be? And as I told you that sort of people beginning, I keep writing something wrong also, just to make sure that you're honest. See what is going on. Limit n tends to infinity. It's already here. Probability in fact limit. So I've already done something really good. So I should remove this.
Just A1 is enough. Everything else is.
Okay, so that is. This is what is called a continuity of probability for increasing events. The statement makes sense. So here this is union. But you should really think of, because AN is smaller than AN plus 1, that is union going up. You can just look at the last event and take its limit. That's what it really means. So this is what is known as continuity of probability. And that is what is being used there to claim eta and one is eta. Maybe remember how to do this. So one axiom which is needed here is that people might not have told you, but this is an axiom needed to define even a function which is called this P function. It's still defining probability to every possible event. So this is an axiom for disjoint PIs. That is PI intersection PJ. This is an axiom. We don't question axioms. Build from it. So this is true. I want this to be true, but here I'm not going to assume the chance because clearly they're not doing. So how do I go from this to this? Is the question. I want to prove that. The only tool I've given is disjoint. So how do I break this up into disjoint things? I do the following. V1 equal to A1. V2 equal to A2 without A1. Right. Now we can visual disjoint. Here we will make it. A minus B2. A3 minus A1 union exit. It must be they're going up. So A1 is contained in A2 anyway. And union of BI is same as union of AI. By definition. Now I'll leave the D is an exercise. Once you observe this, the proof is nice. This is an axiom. From here I want to go to here. And the construction is that BI should be considered in this. This is a good exercise for you to churn your probability and this is what really continuity of probability is. And that implies that theta goes to it. Because these events are exactly this is what is. And this event is nothing but union of Zn equal to 0. So everything on the board is exactly the same. This is the event of my eta. That there exists an n for which Zn equal to 0. Here I am taking the limit of eta n as n goes to 0. And claiming that this to. Okay. So now it is small that yes. Definition now. With this definition, what are the results? So rather, I could have technically written Zn here from my definition. We just slightly sparse notation. What is the definition of Gx? S to the power x. I'm actually taking Zn as a random variable, but rather writing full Zn, I'm just writing n. Okay, so now what do we have? P of x equal to 0 is equal to Gx of 0. That we can verify by very definition. Gx of 0 is nothing but probability of x equal to 0. Fine. What do we need time? Again, by definition.
So P of x equals to 0 and what?
Gx of Gx of 0.
Gx of 0 is basically 0. Just 0. And Tx of 0 is
This was LDBT. These things are by definition. You're not convinced, we good to go back over and one over why it is. At least you pay some attention. Now what are we going to do? We're going to look at, so this is about how process started. This is level. We're going to look at level 1. Okay, and think of this as by definition Z1. Let's say that this was Z1 was equal to I. And I somehow have come to level 10. You see some kind of selection. So if I give you the Z1 equal to I, what can you say about the process going forward? It is as if I am starting from here with I particles. Yeah. And Zn minus 1 as my progress. Makes sense? So rather than starting at one point and looking at depth n, I would say I'm starting at I independent points for I of them and depth n minus. That I get. What's that condition on? That will be. Now we going to write G of this. Pi is nothing but the probability that Z1 takes value I. This is engineering conditioning. Z1. This is clear? Yeah. Because of it. Now use this pattern for potentially translation. That given that Z1 was I, what is this quantity? In terms of Zn minus 1. Exactly what we said. That essentially you're starting I different velocity and looking at a depth of n minus 1. And all of them are independent. That's the beauty of it. So each of these processes is starting from each of these points. So this is let's say so this is one such. This and so on. I of them and all of them are independent. What can I write is in terms of Zn minus 1 and I.
Well, that you have written Z1 equals to I, right? In the
Conditioning Z1 equal to I. Once I know this, I want to write this thing as a function of Zn minus 1 and I. And what do we really have? That I with such processes running in parallel independently, and they have gone to depth of n minus 1. So this should be equal to how do we want to go? Anybody wants to guess?
I guess expectation is the
4 to the power. All of them are independent. That's what really is. This is really the fundament. What we are going to do is and recursion because of this. We're going to increase your level 1. Everything is behaving independently with just one depth less. That's really what. So everything is going to be written as a recursion. Thereafter, it becomes an analytical problem. All the physics is gone. All the math and analytic tools are. Okay. Now, so let me just code that definition. Copy. It worked that way. What the space?
That thing we just scripted from the same period.
So, right. And equal to. So, what did I get? I got from this I G n plus 1 I. The last thing I did, this is what I got. So I want to write this as G equal to x of G n plus s. Any objections to this? No objection. This fine. Look at G n of s is Gx of s. So x, remember, is my number of children at a particular level of this stage. So it is okay. See, Pi is nothing but the number of progeny I get at any given particular. That is what I get. Is everybody on board? There's no magic. This is whatever definition we have, just writing it as that definition. What has happened? Gn minus 1 has come inside the argument. That's all it's happening. So rather than s, you're essentially evaluating at Gn minus 1 of s. And that's what essentially it means. Not okay. I'm still okay. What would be Gx of t? Norm form. Yeah. Just tell me that will clear all your doubts. Gx of t, x is a random variable which is taking value I with probability p of I. So tell me the second term. What multiplies this? Huh? By derivation, this is again this. What have I done? I just taken t equal to j minus 1 of s. Then what I'm pushing to this side. Left hand side is nothing but j. So this is all the value there is. Okay. We are essentially done after this in terms of whatever we want to see as a process. Here after it will all be math. So think about it, what has really happened. And the trick really is that looking at that one small tree there. This is the Gn of s is nothing but starting from 0, the nth process. This can be written as one level down, which takes care of x. So x is here. X will generate the number of children at level 1. And thereafter, each of them are essentially redoing the whole process again. So it's as if you're replicating this particle here, but with X out.
Yes.
That's all that's happening. So that's the recursion which is being written out. That's the concept. Okay, so now how do I solve such an equation? Or what is the solution of this equation mean in terms of what I want? What is the connection of this to eta m or eta? What is the connection of this to eta m or eta? This is the connection to eta m.
Eta m is GM 0.
Exactly. So if I evaluate this at 0, I will get eta m. And I also know that eta m goes to eta and then goes to infinity. So those two facts will actually tell me something about eta itself. So what does it mean? This implies that eta m is gx of eta m minus 1. By definition, if I were to evaluate this at s equal to 0. Evaluating I also know that eta m goes to eta. So as I goes to infinity, I can essentially find a solution. So whatever eta is, this is really that is the solution of this equation. This fixed point equation. So eta that is fine. So for the moment, we're not able to say eta is 1, eta is 0, whatever. But we know that eta is exactly the solution of this equation. And g of x is completely known. Right? G of x is just one single random variable which controls g of x. So now tell me how to go beyond this. Now I want to claim something about when is eta 1, when is eta less than 1. Now this is out of really any physical process. We are given random variable x, we can compute g of x. All I want to find is a solution to such an equation. So far so good? Everybody on board?
The next question.
Next question is how do I solve this? Do I need to solve it? All I want to claim is something about eta less than, sorry, when is eta 1 and when is eta less than. That's all I really want. I don't really care about precisely finding.
So we have the definition for this gx of now. Yes,
Right? G of x is written there.
Yeah.
What kind of function is g of x? As a function of t?
For eta equal to 1, it is always true.
Eta equal to 1, it's always true. Very good observation. So this equation always has a solution at eta equal to 1. Just plug it and see what. Because summation pi is always 1. So g of gx of 1 is always 1. So eta equal to 1 is always a solution. Now question is, something more has to happen. Because otherwise, properly every time I'll get eta equal to 1. So you have to argue that that's the only solution under certain settings. What is that setting? And for that, think about what kind of function g of x is real. Is it an increasing function? As a function of t?
T is greater than 1 by
No, increasing function means as t increases, gx of t also increases.
Oh.
So one thing I know. So property number 1. Because what one way to prove the function is increasing, so get it derivation.
Yeah.
So also convex. Yes. This also is. What more do I want? For to say something. So something is. It's
Or it has equal to 0 if it's trivial.
it is equal to 0.
Oh, 0 is equal to 0.
It's also here. So we can actually show something stronger. That the if the probability x is less than equal to strictly less than equal, then you have really the regime of interest class. Then Gx is strictly and also we are getting for a solution only in integral zero because eta is a probability. This is not. As long as this is true, we just take the second derivative of this point. The derivative is strictly derivative. Direct computation. Okay, so suppose this is strictly convex. What kind of function strictly convex function looks like? And we are interested in 0 to 1. So it's going to look like so 0. This is my 45-degree line. Yes. It has to cut somewhere, that's what it means to have a fixed point. And I know that the function is strictly convex. So what are possibilities of a strictly convex function between 0 and 1? And we know definitely that 1 it cuts it. That also will. So it has definitely one solution. So either the 2 or 1.
Is it 0 or 1?
No, 1 is always there.
Yeah, 1 is always there.
So one more can happen because the first function is strictly convex. Nothing more than that. So either it could look like test. This one possibility is that it is strictly convex. What is the other possibility? It still has to touch one. It has to start here, then this brush this and go, and not touch anywhere on this line. These are the only two possibilities for such a function. So at this point, what can you say? It will tell you something about it having two solutions versus one solution.
So if it tends to one, like
If
if
at
it's a
this point, this function g of x, what property it should have so that you can distinguish between these two possibilities?
What property gx should have?
At 1. So gx of 1 should have two possibilities. One possibility should give rise to this, other possibility should give rise to that.
we should do the derivative of
Correct. So what is the conditional derivative at this point? So if gx prime is greater than 1, gx prime 1 is less than 1. Which of the two is the component? Think about it, right? Greater than 1 means this going above, it has to go out because it's a strictly convex function. It can't go around that line. And the only possibility for this is it's actually less than this. It touches, if it is less, this belongs to setting side this belongs to. We're almost done. Just by this simple math. Because what is gx prime of 1? You noticed If gx of t is this, what is gx prime of 1? So, x. So what the very simple picture like this, what we're able to show is that if x is less than because eta equal to 1 is always the solution. We know that eta satisfies that. And that happens as long as expected value x is there. The other condition, there are possibility of two solutions. I'm going to leave that as an exercise to figure out that the one which is lower is always going to be your solution. Is there a reason? The book I'm following is a standard book, so that I keep you honest. By the next time I actually come back reading this, that's the only reason I'm leaving this. That among the two solutions you're going to get, the lower one is actually the return. See, otherwise you'll get a fallacy. That even though expected value of x is greater than 1, we're still getting eta equal to 1. So you should already see something is going wrong. So there is a good reason why the lower of the two is actually your answer. And because there's nothing but the continuity of probability. That as eta n goes to eta, it touches the first one first. It cannot go beyond that. That's the whole thing. Okay. We're done. Magic happened really. The proof is very simple compared to the implication of the theorem. The proof is rather simple. And one take home message really is that maybe you think of this recursion that did all the magic steps. The recursion was all there. There's nothing else. Once you notice this, it's a matter of writing it down. That is why this process is actually simpler than many more complicated processes you're going to see. There are no correlations across the levels. If you condition on the first level, everything else is happening independently across different, you can call it tree if you want. Across trees, everything is independent. And as you go down, they're all identically distinct. That's really what we do. So this was one step. Second was the continuity of probability. So essentially say that the probability of dying starting from here is essentially the same as probability of dying starting. That's another step we needed. If they were different, these things would not be able. We will not be able to write one as the function of the other. And that is because the tree is unbounded. So it's yes. I think this is very difficult to convince a 10 standard kid. We say, how can they be the same? This is the fact that both are limiting answers. Remember the Resnick-Halliday puzzle? That there are two trains approaching each other at a constant, whatever fixed speed. And the bird flies from top of one train to the second train and keeps going back and forth. How many trips are you going to make until they cross each other or they collide? The answer is infinite. That at least at that level, I never understood what is going on. How can it be infinite? Finite distance, finite speed. How can you make infinite trips? But if you don't understand that, you'll never understand this. So then why should ever be the probability be the same? Starting at level 0 or starting at level 1? The whole point is that as n tends to infinity, eta n minus 1 and eta n, they better look the same. So that's really the problem. If you understand this, the rest of it is just writing it down via this generating function. All right, any questions? Otherwise, let's.
So if I